Find the equation of the tangent line to the graph of f of x equals 1/2 x times the natural log of x to the fourth at the point -1, 0. So in this case, we're looking for the equation of a line, specifically the equation of the line that's tangent to the graph of f of x at the point -1, 0. And since we're looking for the graph of a line, or the equation of a line, we're looking for an equation in the form y equals mx plus b. And we know from our study of derivatives that if we take an x value, plug it into the derivative, the output is a slope. Specifically, it's a slope of a line tangent to the graph of the original function. So this is how the derivative and the function itself are related. So we want the slope of a line, so we want the slope of a tangent line, so we need the derivative of f of x. Now, just looking at this, there's a couple of ways we could go about this. There's no right way to do this problem. You have options. So one thing we could do is take the derivative of f of x equals 1/2 times x times the natural log of x to the fourth. Another option would be to apply the property of logs that allows us to take that exponent out front. So that power of 4 pops out front as a multiple. So then our function becomes f of x equals 2x times the natural log of x. Either way, we're going to get the same tangent line. There's no right way to do this problem. Let's just do it both ways. These derivatives aren't terribly time consuming. So over on the left in blue, it looks like we're going to have to apply the product rule because we have a 1/2 x times a natural log of x to the fourth. And we're going to have to apply the chain rule for that natural log portion because we have this composite function, the natural log of x to the power of 4. All right, so let's apply the product rule first because it applies to the entire function, and then within the product rule, we're going to be using the chain rule. So f prime of x, the derivative of f, is equal to the derivative of the first. So the derivative of 1/2 x is 1/2 times the second, which is the natural log of x to the fourth, plus the first 1/2 x times the derivative of the second. And so for the derivative of the second, we have something of the form ln of u, where u is a function of x. So we could write u of x if you want. So we have the natural log of u of x, and if we want to take the derivative with respect to x, not with respect to u, but with respect to x, and apply the chain rule, we would say that's, well, the derivative of the outer function evaluated at the inner function. So that would be 1 over the argument, or 1 over x to the fourth, times the derivative of the inside, so the derivative of x to the fourth, which would be 4x to the third. Okay, so there's the second part of our derivative. So it would be 1/2 x times 1 over x to the fourth. And I'll simplify the next step, times 4x to the third power. All right, so let's simplify this. It looks like there's a lot of canceling that's going to happen in that second term of our derivative. So f prime of x is equal to 1/2 ln of x to the fourth. And now let's see, we have the 4 and the 1/2 will cancel. That will give us a 2. And then we have x times x to the third, which is x to the fourth, divided by x to the fourth. So all those x's will cancel. So that last term just becomes a +2. So now the slope of the tangent line is f prime of -1. So we're plugging in the x value. So we're looking at the point -1, 0. Negative 1 is our x value, so we plug that into our derivative. So we get 1/2 times the natural log. Well, negative 1 to the 4th power is 1 plus 2. And we know the natural log of 1 is equal to 0, so that first term cancels. So the slope of our tangent line is equal to 2. And now to complete the equation of the tangent line, we could use the point slope form. Y minus y1 is equal to m times x minus x1. So we plug in negative 1 for x, 0 for y, and 2 for m, or negative 1 for x1 and 0 for y1. So we'll have y minus y1, so y minus 0 equals, well, let's put the minus 0 there just to show all the steps. Y minus 0 equals m, which is 2, times x minus x1, which is a minus 1. Let's come down a little bit. So it looks like our equation of the tangent line is y equals, I will distribute the 2. 2 times x is 2x. And we have a minus 1, so that's a plus 1 on the inside. So 2 times 1 would be a plus 2. All right, so there's the equation of our tangent line. Let's see if it's a little bit easier if we apply the power rule for logarithms first and bring that exponent out front. So these two are equivalent. So let's take the derivative of 2x ln of x. So f prime of x is equal to derivative of the first times the second plus the first times the derivative of the second. The derivative of ln of x is 1 over x. No need for the chain rule here. All right, so it looks like f prime of x is equal to, oops, I forgot the x there, 2 ln of x plus 2. Again, those x's, the x and the 1 over x cancel. All right, so we're about in the same place as we were before, just a little bit simpler. And now we can't plug negative 1 into x in this form. So let's bring this 2 back up top. So f prime of x is equal to ln of x squared plus 2. And that's exactly what we have here. Well, if we were to bring the 1/2 up, we would get ln of x squared plus 2. And then I'm not going to repeat the exact same steps, but then we would end up at the exact same equation of the tangent line. Let's zoom in a little bit so we can get the whole problem. Okay, so that's it. Usually simplifying using properties of natural logs, or logs in this case, or any sort of algebraic simplification first, usually streamlines the problem, sometimes slightly, sometimes a great deal. But in this case, I don't think it's much of a difference either way. Okay, that does it for this problem. I hope it was helpful.